Similar. All right. A little bit. All right. So guys, I want you to notice right here that if AB is an element in function A or relation A, then the opposite of that, BA, will be in function B or relation B in this case. All right? And what I want you to know is this. Just look at this right here. If you plug in a 1 into relation 1, you get out a 5. But for B, it's the other way around. You plug in a 5, you get a 1. That happens over and over again. If you plug in a 2, you get a 6. But if you plug in a 6, you get a 2. In function A, if you plug in a 3, you get out a 7. But in B, if you plug in a 7, you get out a 3. That's how you know that they are inverses of each other. Can you generalize basically what you're doing right there? What are you doing with the X's and the Y's? Switch them. All you're doing is switching, right? And that's what we're going to do, is we're going to switch things. Okay? So let's look at this triangle, please. All right? My directions for you are to determine the inverse of the following relation, then graph the relation and its inverse and compare. So we're going to find the inverse of this triangle, and then we're going to graph both the triangle and its inverse, and we're going to start comparing them. That's what our job is. So let's just start with the triangle first off. I want the inverse of triangle ABC. Now I'm going to show you a new notation. Oftentimes when we deal with functions and relations and inverses, we'll use this symbol right here to represent an inverse. What does that look like to you? Looks like a negative exponent, doesn't it? It's not. Okay? In this situation, this means it's an inverse. Okay? It means it's an inverse. We normally only use this when whatever's underneath it is not a number. Okay? If that was a number or a variable, then yeah, it would be an exponent. But this is not. This is trying to represent triangle ABC. Or maybe it's function. Sometimes we talk about the inverse function. Okay? Now that doesn't mean take x to the negative 1 power. That means do the inverse of this function. So that's a new notation for us. Alright? So anyways, help me with what these new points are going to be. Instead of the point negative 3, 4, it's going to be 4, negative 3. Good point. Instead of the point negative 3, negative 2, it's going to be negative 2, negative 3. Good. And instead of the point 4, negative 2, it's going to be negative 2, 4. So far, so good? Not difficult, right? All right. What I want to do is I want to graph these now. So I'm going to start with my first. I'm going to start with my triangle ABC. You know how to graph as well as I do, so go ahead and do that.
What's that little thing next to that ABC?
I want you to notice, now that we have them graphed, I want you to notice, is there any kind of relationship there? Do you notice similarities or anything? What's the deal with them? Okay, they are both right triangles. Do you think they're the same triangle?
No.
By the same, I mean the same size. Count the sides, they are. Count the distance from A to B, and A to B, and then A inverse to B inverse. They should be the same distance. Okay. I'm going to draw a line for you, and let me tell you if this line helps. Tell me if this line helps you. Does that line help determine a relationship?
No.
What are these two triangles doing? They are symmetrical. Do me a favor. Rotate your paper so that AC or CA, rotate your paper so that AC or CA is horizontal. So just about a quarter turn counterclockwise.
What? I don't know.
All right.
Oh, that's the inverse.
All right. This line is y equals x. And that should be very familiar from last night. Because wasn't that the whole point last night? If you make a composition, don't you end up with y equals x? So this right here, y equals x, is the inverse. What we just found out is that's not the way I want to say that. inverse functions reflect over the line y equals x. Okay, we're going to skip that other triangle just because of time, but we're going to try the quadrilateral here, Wxyz. Now, we can graph this, right? Okay, before we graph it, though, I want to go ahead and find... Yes, ma'am.
Thank you.
I'm going to go ahead and find the inverse here. So let's find the inverse of Wxyz. So what would be my new points?
4, 1.
Well, start at the beginning.
5, 3.
-5, +3. And then 4, 1. And then 4, -2. And -5, -5. That one doesn't even change, does it? Okay. Can you graph those? Of course you can. So take just a moment to graph those.
Where does that say Wxyz?
Okay, guys. So as you can tell, once you get all this graphed, you can see that the original trapezoid, Wxyz, and the inverse of that trapezoid, they are a reflection over this line y equals x. Okay? So they do reflect over that line, and it's important for us to recognize that. Okay? What we're going to do now is we're actually going to look. We don't often actually get shapes and polygons, although we can. We're dealing more with functions, so we need an equation, don't we? So let's do another problem with an equation. First off, this is not a new function. This is an old function. What's a quick and easy way to graph this particular function? Slope-intercept, right? Do you recognize mx plus b, right? So let's do that. Take just a minute to graph that. Of course, you know you're going to start at 1, and then go up 2 over 1, up 2 over 1, up 2 over 1, and make yourself a line. So that's just basic old Algebra 1 graphing a line. Now, I'm supposed to graph its inverse, but I didn't give you anything else. That's all I gave you. So what am I going to do? How can I think about this inverse? I'm going to come back to your way in a minute, but yeah, I know where points are, so let's just switch them. Let's see, I started with the point 0. That's the wrong button. How about this? Here we go. 0, 1. What is that point going to change to? 1, 0. I have the point 1, 3. What's it going to change to? 3, 1. So is this doable? This isn't hard, is it? I've got the point 2, 5. We'll switch to 5, 2. And I can definitely graph these now, right? So let's just do that. And Tyler, that was a good idea. I can't wait to get to this other method, though. And does that look like it's a reflection? Sometimes it's hard to tell unless you have that line y equals x. I like to always draw that line y equals x because to me it's way clearer when you can see that. And yes, it is. It's definitely a reflection, isn't it? So were we able to graph its inverse? Now what's the one thing I don't know though? Can anybody tell me the equation for that red line? I have the equation for the black line. The black line was given to me as y equals 2x plus 1. I wish I knew the actual inverse of it. Okay, I've got y equals... Okay, I've got a couple different answers, and I agree with, I'm hearing your answer, x minus 1 over 2, but where did you get that from? Okay. All right. I think he's looking at this, and he says, this says plus 1, so I'm going to do minus 1. This says times 2, so I'm going to do divided by 2. And I do like his answer, but you know what? Maybe we didn't notice that. So let's think about this for a second. All right, isn't this a line? Can we use slope-intercept form? Or even point slope? Could we use point slope form? We could use either one of those. What's the slope of this line? It's definitely 1 over 2, isn't it? Up 1 over 2, up 1 over 2, up 1 over 2. So my slope is 1/2. And what's the y-intercept? I believe it's a half, isn't it? Negative a half? So I think it's going to be minus a half. Now, are these two the same? Yes, they are. Okay? But of course, that was a lot of, this was us using our slope-intercept skills. This was somebody who thinks they kind of figured it out and they did a good job. But I'd like to have a concrete method that works every single time for coming up with an inverse. And that's what we're going to do next, is I'm going to show you how to get that every single time. Okay? So just like we switched the x and the y points on all of the previous relations, we're going to switch the x and the y here. Now, another name for f of x is what? Y. So I can just take this out and make it a y. Okay? And now we're going to switch them. So I'm going to put the y on this side and the x on this side, and it looks like x equals 3y minus 1. So now I'm just going to solve for y. How would you solve this equation for y? Add 1 to both sides. That gives me 3y equals x plus 1. And then divide by 3. And I can actually leave this in two different ways. I can either leave it as x plus 1 over 3. Or, if you recognize this as being a line, you might want to change it to 1/3 x plus 1/3. But those are both the same thing, aren't they? This one actually makes more sense as being the inverse of this, doesn't it? Because look at the original equation. The original one was 3 times a number, subtract 1. Well, this one is plus 1 divided by 3. Aren't those all opposites? A plus 1 here and a minus 1 here. A divide by 3 here and a times 3 here. So these look like they might be inverses. There's two ways for me to check that they're an inverse. The way you did it last night and the way we did it a few problems ago. How could I check that they're inverses by graphing? All right. If I were to graph both of these equations, this one and this one, they should be reflections over this line. Or I can do it like last night, and I could do f of g and g of f, and both answers had better equal x. Whichever way you'd like to do it. I think I got a piece of graph paper. We're just going to graph it. I want you to graph it tonight anyways. So let's see. If I graph, the original line is 3x minus 1. So I start at minus 1, go up 3 over 1, up 3 over 1. Make myself a nice pretty line. And then I graph my inverse. This one's a little bit trickier, right? Because the y-intercept is 1/3. But that's going to be, where am I? Right there, right? So I could do my 1/3 there. Or, that's a good point, I could just switch all these points, couldn't I? So why not switch all the points? Okay. I think I'm going to do the slope-intercept form, though, just to make sure that my equation does match the way it's supposed to. So, although the switching points would probably be easier. So let's see, there's a third, and then up 1 over 3, then up 1 over 3 again. And it's not quite as exact, but does it look like a reflection? I feel pretty good. If it looks like a reflection, I feel pretty good. So just to save a little time, I'm not going to graph these, but I know that I could. I'm just going to find the inverse. So remind me once again, how do you find the inverse? You switch x and y. So put this over here and put this over here. That's supposed to be an x. So how would you get y by itself?
So
That's right. So subtract the 3. And that gives me negative 1/2 y equals x minus 3. And then, how do you get the negative 1/2 to go away? Yeah, multiply by negative 2. Right? And that's going to give me y equals negative 2x plus 6. So this should be, that is f of x inverse. Okay? Now I know I used the letter y, but this would be f of x inverse. Okay? And of course I know you could graph these, and if you graphed them, they should definitely reflect over this line. Okay? I missed the line a little bit, a little sloppy, but that's the idea.